Burn a peanut in the calorimeter, heating some water. So 100 milliliters of water is 100 grams. And you're heating from 22.3 to 35.4 degrees C. So the change in temperature is, what, 13.1 degrees? Yeah, okay. So then how do we figure out the amount of heat produced? Yeah, you multiply by the amount of water that was heated up. So 13.1 degrees C times 100 grams gives you 1,310 calories. Yeah? All right. So then it asks for the energy density of the peanut. The energy density is going to be the calories per gram. So that means 1,310 calories divided by the mass, which here is given as 0.5 grams. Okay, divided by a half is the same as multiplied by 2. So that's 2620 calories per gram. Yeah? All right, good. Okay, and then the sum question. The label for the peanut says there are 13 calories, big C calories, in a 5-gram serving size. What was your measurement above accurate? Why or why not? Well, to figure this out, we have to get them in some kind of comparable form. So 13 calories is 13,000 little c calories in 5 grams. Okay. And that gives us 2,600 calories per gram. So we compare that to the calories per gram that we calculated in the calorimeter. We got a little bit more, 2,620. So you could say it's reasonably close, or maybe you thought that was way too far off, so that was far off.
What if you divided the 13 by 5, you get 2.6, but you knew you had to move it down?
Yep, yeah. This is the same thing as saying 2.6 big C calories per gram. So as long as you didn't say, well, this only came out to 2.6, so I way overestimated it. As long as you saw that those were reasonably comparable numbers, that's fine. So if you said something about that, that's all I was looking for. Is that okay? Mostly. All right. Let's talk about nuclear chemistry. Here's a graph. This actually comes from your book, of all the sources that you get exposed to radiation. So you'll notice that the vast majority of that are natural sources. From radon, which is an element number 86, around. We've got cosmic rays, which are rays that come from outer space, make it through our atmosphere and hit us. You've got internal sources of radiation. There are atoms inside you that are radioactive, that produce radiation. And then, of course, in rocks and soil and all the, when we mine radioactive stuff, it comes from the earth. So then you've got a small percentage, 18%, things that we do to ourselves or that we expose ourselves to increase that. So things like medical x-rays is the biggest ones. If you get a CAT scan or a CT scan, something like that, that exposes you to a lot of radiation. Relatively a lot. Nuclear medicine, if you're getting treatments for cancer or labeled things, contrast dyes and stuff. Sometimes they're radioactive fluorescent dyes. And then some consumer products and various other things. So the vast majority of radiation we're exposed to is not some kind of dangerous equipment or something. It's actually just because radiation is all around us and we encounter it all the time. Now that said, there are ways that radiation can be more or less dangerous, and we're going to talk a little bit about that today, and I brought some examples. But something like radon, for example, radon will expose you to radiation, but it's actually not that dangerous until you get it inside your body. When you inhale, it's a gas. a very heavy gas. When you inhale it, then you have something radioactive inside your lungs attacking stuff inside your body, and that's a problem. If you're not inhaling it, less of a problem. So that's why we always test houses and such for radon. But now let's actually define what we're talking about here, and then we'll get into some of these examples. So when we talk about radioactivity, what we're really talking about is a few specific processes known as nuclear decay. Now, some atoms are naturally unstable, and so they decay, they fall apart. And when they fall apart, they release various particles, and those particles are known as radiation, radioactive particles. So here's some examples of what that might look like. And we're going to revisit some of this notation that we've talked about before. So let's look at radon. If I write an atom of radon like that, what am I saying? What do those numbers mean? Yeah, the atomic number on the bottom, 86, and then the atomic mass of a specific isotope, 222. So that means we've got 86 protons and what, 100 and some neutrons. What is that? Why can't I do that math right now? Somebody do that. 126? 136, yeah. So 86 protons, 136 neutrons. I haven't had my coffee yet. And radon is an unstable nucleus. This radon-222, we say, doesn't just hang around like that. It actually decays. And when it decays, it loses a particle that has two protons and two neutrons. We call that an alpha particle. But interestingly, a particle with two protons and four neutrons is also an atom, right? It's actually helium. Helium has two protons and two neutrons. So, I'm sorry, 4 overall mass. So an alpha particle can also be thought of as just a helium nucleus. And that's a certain type of radiation, alpha particles, a beam of alpha particles, and we're going to see some alpha emitters in a minute. All right, so then what happens to the radon if it's released this alpha particle? How do the numbers change on the radon nucleus? Yeah, and so this works just like a chemical equation. You can't lose stuff. You can't make stuff magically disappear, although we'll see in some cases now you can. But these numbers still have to add up to 86 and 222, which means we now have a particle that has a mass of 84 and 218. Okay, it's lost 2 neutrons, and 2 protons. So 2 from its atomic number, 4 from its atomic mass. Is that still a radon particle?
No.
It's not. What is it now? PO, polonium. So this is very, very different from what we have seen before in chemical equations, because one type of element is actually becoming another type of element. And that's not something that happens in chemical equations. That only happens in nuclear equations. So this is known as alpha decay. And it's a very common type of nuclear decay. So, all right, decay is beta decay. Oh, let me show you a picture of this first. Sorry. So this is what alpha decay actually looks like. You've got a radon nucleus full of protons and neutrons. It ejects this alpha particle, and then you end up with what you had. Okay. Next, we're going to look at beta decay, which is kind of interesting because it's alpha decay. I think is straightforward. You have this nucleus, some stuff goes out, you have less stuff. Beta decay is a little bit different because you actually lose an electron, and it ends up kind of looking like you have more stuff. So let's look at this equation. Here's the equation for a beta decay. you take hydrogen 3, which is not the normal nucleus of hydrogen, which is hydrogen 1. This is known as tritium. It's used in things like exit signs, in watches sometimes. And what this will do is decay to produce a beta particle. Now, a beta particle is an electron. So we draw an electron like that. It has a -1 charge and no protons or no neutrons or anything. And this is known as a beta particle. And then remember, those numbers still have to add up. So what we end up making is something with 2 protons and 1 neutron. So essentially what happened, and that, if you look at what that is, that's actually a helium-3 nucleus, because the two protons tell us it's helium. So essentially what's happening here is that a neutron, which is 1, 0, has no charge, but it does have a mass of 1, is kind of splitting up its charge and becoming a proton and an electron. And then the electron is being emitted. So it's sort of like a neutron is converting into a proton and losing an electron in the process. Here's a picture of that. Oops. So there's your hydrogen nucleus with a proton and 2 neutrons. Then it loses the electron and ends up a helium nucleus with 2 protons and a neutron. So that's known as beta decay. And beta decay, beta particles are much smaller. An electron is much smaller than a large helium nucleus. They're faster, and they have more penetrating ability. They can get through stuff more. One of the things you need to be able to do from these is draw these decays. So if I say this type of element decays by this type of process, draw an equation for that. So we're going to look at 2 other ways in which these things decay. Let's number them to keep track of everything here. So we've got alpha decay, we've got beta decay, we've got gamma decay, which doesn't have an equation associated with it. And then the 4th one we're going to look at is called positron emission. In positron emission, we deal with this strange particle that we've never really talked about before, the positron. And you don't really encounter it except for nuclear stuff. A positron is a particle with the same mass of an electron but the opposite charge. And it only exists for tiny, tiny, tiny fractions of a second. Because as soon as it encounters an electron, and electrons are everywhere, it collapses and is no longer around. So the equation looks like this. It's a weird looking equation, and then we'll talk about what it means. You can take something like fluorine, fluorine 918, and it emits a positron, which is the same as an electron but with opposite charge. And it also then forms an oxygen 18 atom. So the math kind of adds up there. But the thing that's weird is that from looking at the numbers, it looks like you're emitting a proton. Right? Like the 9 proton is being emitted. But you're not actually emitting a proton, you're emitting a positron. Because if you were emitting a proton, which has a mass of 1, this number would go down to 17. So what's happening here, and I seem to have lost my colors. What's happening here is that it actually does emit a proton. And the proton turns into a neutron and an electron. The electron, or I'm sorry, a proton and a positron. Not an electron, a positron. The positron is emitted, and the neutron is reabsorbed. So the atomic mass of this stays the same, even though it's lost some positive charge. Positrons are not detectable like this because they hit electrons and simply disappear. So they don't kind of produce any kind of damaging particles, but it is a mechanism by which things can decay. We're going to talk about decay in a minute. And then the other way, the fifth way, the last one, is called electron capture. And electron capture is just what it sounds like. You add an electron, but an electron is negatively charged, so it ends up actually causing the atomic number to go down. So radioactive iodine actually decays by electron capture, which means it gets an electron and then its atomic number goes down by 1. So in this case, iodine, which is 53, becomes tellurium, which is 52. There's a nice table in your book here that summarizes these. Tells you what kind of particle is decayed, how your particle mass, what size your particle mass is, the charge of the particle, and then the change in the numbers. Either the nucleon number, which is the upper number, or the atomic number, which is the lower number. So that might be a nice way to summarize those. And then what you need to be able to do, so what we'll practice here, is write balanced nuclear equations for these sorts of things. So everybody try these couple. Using those things that we just wrote down, those processes that we just talked about, draw nuclear equations for these 4 processes. First one, plutonium-239. Decays by alpha decay. Now, putting the number on the lower left is actually redundant because the number corresponds to the element, right? So if it's plutonium, if it's Pu, we know it's got to be 94. It can be helpful to put that down there, but sometimes you won't see that. So if it decays by alpha decay, how'd you do this? Yeah, so put your alpha particle first, and then do the math. If it loses 2 on the lower number and loses 4 on the upper number, then the leftover thing must have 92 down here and 235 up here. So then you look at that 92 and you realize that that is uranium. Yeah? Because in the question, it's telling you about a specific isotope, plutonium-239. Yeah. Yeah, you'll notice on the periodic table, elements like plutonium, those ones on the bottom, the ones that are outlined, that outline means they're radioactive. And since they're radioactive and they do this decay, you can't have an average mass of the isotopes because the average is always changing as things decay more and more. So all you have instead is a number of parentheses, which is either the most stable isotope or the most common isotope, depending on the table. Okay. Second one, Protactinium-234. Decays via beta decay. So same thing, you're going to put your beta particle here, your electron. And then what does that mean is left over here? Right. So nothing, no change up here. because a neutron is turned into a proton and an electron. So that actually, see that. Third one, carbon-11 emits a positron when it decays. So carbon is 6 and then 11. So there's its positron. And that means it's left over at nitrogen, right? Oh, boron, I'm sorry, yeah. You're right. Okay. Then the last one, carbon-11 undergoes electron capture. So that way an electron is on the left of the equation. It's capturing in an electron. Right? And so then what do we come out with? That same boron 11. So those are the nuclear equations. All right, you got those. All right, yeah.
So basically, you just have to memorize like the decay.
Yeah, what those 4 different processes are, and you can kind of guess it from the names. You know, alpha decay means you're losing an alpha particle. Beta decay, a beta particle, and so on. And then gamma decay, we don't draw the equations. It just emits gamma rays because there's no change in the nucleus. Okay. Okay, so the second part of nuclear chemistry is dealing with how this decay actually works over time. So something like this, if you look at a particular sample of a radioactive element like iodine-131, you'll see that over time, its decay looks something like this. So if you start with 16 milligrams, then after 8 days you've got 8, after 16 days you've got 4, 32 days you've got 2, and so on. And this is known as the half-life. So I don't know if you've heard this term before. Not related to video games. But half-life is the time it takes for half of a sample to decay. So something with a very, very short half-life decays very, very quickly and is not going to be around for very long. Something with a very long half-life is going to be around a long time. And one of the things I'm going to ask you to do is to calculate both the half-life given some data and how much would be still around after a certain time. So, for instance, well, here are just some numbers to throw out there. Half-life of tellurium-128, which is the most common isotope of tellurium, is 8 times 10 to the 24th years. So, like more years than the universe has existed. And beryllium-13, which is an isotope of beryllium, is 10 to the minus 21 seconds, meaning it's gone in such a tiny fraction of a second, we can't even process that. So rather than going through all these calculations first, we're going to do this activity, and then we're going to do the calculations in context of the activity. So what you're seeing here is that each half-life you reduce by half. And we can describe that in this type of equation. One over 2 to the n, where n is the number of half-lives. So in one half-life, n equals 1. After one half-life, you have half left. After 2 half-lives, you have how much left? Yeah, half of that, a quarter, right? After 3 half-lives, you have 1 over 2 to the third, which is 8, so 1/8 left. And so knowing how much we start with, then, we can figure out how much we have left. So here are some problems that will use this. We're going to look at a sample of silver 112. Okay. A 10-gram sample decays to 2.5 grams in 12.4 hours. And the question is, what's the half-life? So a 10-gram sample decays to 2.5 grams in 12.4 hours. What's the half-life? To do a problem like this, you have to figure out how many half-lives have happened. If a 10-gram sample becomes 2.5 grams, how many half-lives have there been? 2, right? So this is, I gotta go get my cord. So 10 grams to 2.5 grams is 2 half-lives. So let's see if we can finish that problem while I get my power cord for the computer. All right, so what did you come up with as the half-life? 6.2, or half of that, right? 12.4 hours is 2 half-lives. Then 6.2 is 1 half-life. Okay. Next one. I'll give you a little less help with this one. We're going to look at strontium 90, which is one of the elements that we looked at in the decay here. The samples there. Strontium 90 has a half-life of 228.5 years. Yeah, 28.5 years. So a 64-gram sample decays to what after 285 years? So the first thing you have to figure out is how many half-lives is 285 years, which is how many? That's 10 half-lives. All right, 28.5 times 10 is 285. So this must be 10 half-lives. All right. So if we started with a 24-gram sample, that means what we have to do is cut it in half 10 times. Oh yeah, I'm sorry. 64-gram sample. You're right. We have to cut it in half 10 times. So you can do that manually. You can go divide by 2, 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 10 times. Or you can look at the equation we saw before, and you can say 1 over 2 to the 10. That's the fraction of the original that we're going to have. So 1 over 2 to the 10th times 64 is this one does it? Let's see. Should be 0.0625 grams. So not much left after 10 years, or after 285 years. Okay. What? Yeah. Try to get some numbers here. Sorry, hold on. Okay, so here's one about brain cancer. A patient is given 48 milligrams of technetium-99, which is a radioactive element, number 43. And that has a half-life of 6 hours. How much will remain after 36 hours, so a day and a half? So everybody try to get a number for this one on your own, and then we'll talk about it.